Semiconductor Packaging. John D. Thomas, Alex Ruth. Book 3, Section 1, Chapter 5, Topic 3. The Influence of Trace Layers on Heat Transfer in Semiconductor Packaging. Introduction. Semiconductor packaging involves intricate layers of materials and interconnects to protect and connect the delicate semiconductor components. Among these layers, trace layers play a crucial role in facilitating electrical connectivity. However, they also have a significant impact on heat transfer within the package. This overview explores how trace layers influence heat transfer in semiconductor packaging, examining their role, characteristics, and effects on thermal performance. Understanding trace layers in semiconductor packaging. Trace layers, also known as interconnect layers or wiring layers, consist of conductive paths that connect various components within a semiconductor package. These paths are typically composed of materials such as copper or aluminum and are patterned onto the substrate using lithography and etching processes. Trace layers serve as conduits for electrical signals, enabling communication between semiconductor components, such as integrated circuits, ICs, resistors, and capacitors. Impact of trace layers on heat transfer. Thermal conductivity. The thermal conductivity of trace layer materials directly influences heat transfer within semiconductor packages. Materials with higher thermal conductivity, such as copper, facilitate more efficient heat dissipation compared to materials with lower thermal conductivity, such as aluminum. Therefore, the choice of trace layer material can significantly affect the thermal performance of the package. Thermal resistance. Trace layers introduce thermal resistance along the heat transfer path within semiconductor packages. As heat flows through the trace layers, it encounters resistance due to the material's thermal conductivity and the thickness of the trace layer. Higher thermal resistance impedes heat transfer and can lead to thermal bottlenecks, resulting in localized hotspots and reduced thermal performance. Heat spreading. Trace layers can aid in the spreading of heat within semiconductor packages. When heat is generated by semiconductor components, it propagates laterally through the substrate and trace layers. The design and layout of trace layers influence the distribution of heat within the package, impacting temperature uniformity and the risk of thermal-induced failures. Conduction paths. Trace layers provide additional conduction paths for heat transfer within semiconductor packages. Heat can flow through the trace layers from the heat-generating components to the package substrate or to external cooling solutions, such as heat sinks or thermal vias. The layout and configuration of trace layers determine the effectiveness of these conduction paths and dissipating heat from critical components. Optimizing trace layers for enhanced heat transfer. Material selection. Choosing trace layer materials with high thermal conductivity, such as copper, is essential for optimizing heat transfer within semiconductor packages. Copper offers superior thermal conductivity compared to alternative materials, enabling more efficient heat dissipation and reducing thermal resistance. Thickness optimization. Optimizing the thickness of trace layers is crucial for balancing electrical performance and thermal management. Thicker trace layers offer lower electrical resistance but may increase thermal resistance, while thinner trace layers provide better thermal conductivity but may compromise electrical performance. Therefore, careful consideration is required to achieve the desired balance between electrical and thermal characteristics. Layout and design. The layout and design of trace layers play a significant role in heat transfer optimization. Design considerations, such as trace width, spacing, and routing, influence heat dissipation, heat spreading, and thermal uniformity within the package. By optimizing the layout and design of trace layers, engineers can mitigate thermal bottlenecks and improve overall thermal performance. Integration with thermal management solutions. Integrating trace layers with external thermal management solutions, such as heat sinks, thermal vias, or liquid cooling systems, enhances heat transfer capabilities. By strategically positioning trace layers and optimizing their connectivity with thermal management solutions, engineers can maximize heat dissipation and ensure efficient thermal management in semiconductor packages. Conclusion. Trace layers are integral components of semiconductor packaging, facilitating electrical connectivity and influencing heat transfer characteristics. Understanding the impact of trace layers on heat transfer is essential for optimizing thermal performance, mitigating thermal issues, and ensuring the reliability and longevity of semiconductor devices.
By carefully selecting materials, optimizing thickness, and designing layout configurations, engineers can enhance heat transfer within semiconductor packages and enable the development of high-performance electronic devices across various applications. Thanks for watching.
Please like, share, and subscribe.